Continuing with the Lagrange's multiplier, solve the example P cot x plus Q cot y is equal to cot z. Now comparing this equation with the standard form PP plus QQ is equal to R and writing the auxiliary equation dx by P is equal to dy by Q is equal to dz by R. P is cot x, Q is cot y and R is cot z. So comparing the two terms, dx by cot x is equal to dy by cot y. The reciprocal of cot x is tan x, so we have tan x dx is equal to tan y dy. On integration of tan x is log secant x. Similarly, integration of tan y is log secant y. For the convenience sake, I'll take the integration constant as log c. Or this is equal to secant x divided by secant y is equal to b, one of the solution. Similarly, considering either the first or the third term or the second and the third term, I have considered here for this example the second and the third term. I get secant y upon secant z is equal to d. Combining both the solution of the PDE will be phi of secant x by secant y comma secant y by secant z is equal to 0. Similarly, consider the second example y minus zp plus z minus xq is equal to x minus y. Writing the auxiliary equation dx by p is equal to dy by q is equal to dz by r. That is dx by p is equal to dy by q is equal to dz by r, where p is equal to y minus z, q is equal to z minus x and r is equal to x minus y. For this example, seeing the denominator term, we have one positive y and one negative y, one negative z, one positive z, similarly one negative x and one positive x. So, for the convenient purpose, I'll choose the multipliers as 1, 1, 1 and adding them. Adding the terms, I get dx plus dy plus dz upon y minus z plus z minus x plus x minus y. The numerator remains as it is, denominators become 0. Please note that here this term is not considered as infinity. We are only eliminating the denominator term. So, writing the numerator as it is and integration, and on integration I get x plus y plus z is equal to c as one of the solution. Again, choosing the multipliers as x, y, z, that is multiplying the first term dx by p by x, similarly multiplying the second term dy by q by y and the third term dz by r by z, and adding up I get x dx plus y dy plus z dz is upon xy minus xz plus yz minus xyx plus zx minus zy. And this term, all the terms cancel in the denominator, so I am only left with x dx plus y dy plus z dz upon 0. Again, this on integration I get x square plus y square plus z square is equal to d. So taking the first function and the second function together, the solution of the PDE will be phi of x plus y plus z comma x square plus y square plus z square is equal to 0. Now there is another example here. Solve x square minus y square minus z square p plus 2xyq is equal to 2xz. So writing in the standard form, dx by x square minus y square minus z square is equal to dy by 2xy is equal to dz by 2xz. I'll first consider the second and the third term where 2x are common. So on cancellation, I'll have dy by y is equal to dz by z. This on integration gives log y is equal to log z plus log c. Further on simplification, this gives y upon z is equal to c or y is equal to zc. Now here again choose the multipliers x comma y comma z. So we have x dx plus y dy plus z dz upon x cube minus xy square minus xz square plus 2xy square plus 2xz square. On simplifying, this becomes x dx plus y dy plus z dz upon x cube plus xy square plus xz square. Taking out x common from the denominator term, I have x dx plus y dy plus z dz upon x into x square plus y square plus z square. Now, this term can be compared with either the second term or the third term. So, comparing this term with the second term, I have dy upon 2xy is equal to x dx plus y dy plus z dz upon x into x square plus y square plus z square. On simplification, this becomes dy by y is equal to 2x dx plus 2y dy plus 2z dz upon x square plus y square plus z square. Now this 2 is from cross multiplication. This on integration gives log y is equal to log x square plus y square plus z square. Here take the substitution, x square plus y square plus z square is equal to t. So this on differentiation, 2x dx plus 2y dy plus 2z dz is equal to dt. So we have y upon x square plus y square plus z square is equal to d, the second function. Combining the first and second function, the solution of PDE will be y by z comma y upon x square plus y square plus z square is equal to 0. Again consider another example, mz minus ny dou z upon dou x plus nx minus lz dou z upon dou y plus mx minus ly. Remember, dou z upon dou x is equal to dou z upon dou x is equal to p and dou z upon dou y is equal to q. So considering this and choosing the multipliers L, M, N and simplifying, I get the first function as, so I got the first function as Lx plus My plus Nz. Again choosing the multipliers x, y, z, multiplying and simplifying it, I get the second function as x square plus y square plus z square is equal to d. Combining both the first and second function, the solution of the PDE is phi of Lx plus My plus Mz, x square plus y square plus z square. One more example, y square zp is equal to x square zq plus y. Now rewrite this equation as y square zp minus x square zq is equal to x square y. Then writing the auxiliary equation, dx upon y square z is equal to dy upon minus x square z is equal to dz upon x square y. Choosing any two terms initially and simplifying, I get the first function as x cube plus y cube is equal to. Again choosing the other two function, the second function will be y square plus z square is equal to d. Combining both, the solution of PD will be given by phi of x cube plus y cube, y square plus z square is equal to 0. Now these are just the hints I have given what all the multipliers can be. They can be x, y, z. Sometimes they can be 1 by x, 1 by y, 1 by z. Or it can also be 1 upon x square, 1 upon y square, 1 upon z square. Sometimes it can be x minus y, z, or xy minus z. Or it also can be minus x, y, z, or all can be negative depending upon the question. It also can be 1, 1, and furthermore we can also choose dx minus dy is equal to dy minus dz is equal to dz minus dx. All these are valid multipliers.